Okay.
So you didn't record, Henry?
Well, I guess we just got the request from Vadim to record.
Oh, okay. Yeah, it was a good talk then.
Yeah, well. Okay, our next speaker is Rudy Raymer from JP Morgan Chase, and he will be telling us about quantum relaxation for probability optimization.
Thank you very much, Mark. Thank you for inviting me to give me a chance to present our work here. I'm Rudy Raymond. I joined JP Morgan Chase about 1 year ago. Before that, I was at IBM Research in Tokyo. And yeah, I'm very honored to be able to present a series of our work on trying to use quantum algorithms. Here we call quantum relaxation for combinatorial optimizations. So I'm now working as try to find this quantum computing applications for our tasks in the firm. So, okay. And I think one of the application of quantum algorithm or quantum computing is combinatorial optimization. And again, I thank you for coming. And if you want to see more about our group at JP Morgan Chase, you can scan the barcode. And also, if you have questions, you can contact me by this email. And yeah, this is like really purely research. We don't do some financial things. So this is just a disclaimer. And yeah, this is all about JP Morgan. I will leave it there. So that's the end. I have fulfilled my obligation. Okay. So all of this work is based on this following several series of papers that I've been working with my college in Japan before coming here. And recently with my college here in the US, Zichang, he presented 2 weeks ago in Inform's combinatorial optimization meeting, and also other work. I work with IBM Research Tokyo researcher, also with student at Singapore Management University, SMU in Singapore, also some other researcher at Keio University, also with later I also present some of their work that we try to implement these algorithms together. Okay, so this is the summary of what I'm going to present. First is I'm going to talk about this, what is called QAOA, which is quantum approximation optimization algorithms. And we believe this is one of the most promising heuristics for combinatorial optimization problems. And the idea of this QAOA is like, we try to find a solution of combinatorial optimization problem by encoding the solution as a ground state of a diagonal Hamiltonian. And for that, we need to use 1 qubit for 1 variable. Usually it's binary variable. It's like decision of 0 or 1, yes or no. And I'll try to argue with this presentation, during this presentation, that there's a algorithm called quantum relaxation, which I believe is a generalization of QAOA, where in this, you don't need to think about diagonal Hamiltonian. We can encode solution of our problem into the ground state of non-diagonal Hamiltonian. Well, you can extend it to diagonal Hamiltonian. And this is based on this quantum information primitive called quantum random access codes, or QRACs, and where we can use a qubit to encode up to 3 binary variables there. And this is like kind of the earliest quantum advantage known in quantum information, this QRAC. And it has several nice properties, because even with the first presentation mentioned about this noisy quantum device, limited number of qubits. But by using this quantum random access code, we can scale the instance of combinatorial optimization we can solve with limited number of qubits. And we do have theoretical guarantees on these optimization properties. And it seems to be, when we run this on several problems, standard benchmark in classical optimization, the heuristic seems to be compatible to the best classical solvers. Okay, when I talked to my supervisor, I was at McGill 20 years ago. He was an expert in combinatorial optimization, and said, like, okay, what's the state of the art, this quantum optimization at the moment? We say, oh, we can solve up to 10 max cut, not a graph with 10 nodes or several hundred. And they say, okay, you look at this classical, they already can solve traveling salesman problem on galaxies, billions of galaxies, even before we have the spaceship. So it's called Galaxy TSP, right? So they solve like, well, traveling salesman problem is a problem where a salesman start from a city, go around the tour, all the possible cities, and get back to the original position with the shortest distance, right? And all the classical solution can only attack billions of cities, well, stars. I think like Concorde, I think once developed by University of Waterloo, can only solve it with several 10,000 cities, for example, which is more realities. But if we look into it, actually what they do is actually there's some relaxation there. They also apply this divide and conquer. They don't try to attack it with brute forcefully using all the qubit or all the bits, for example. So they do divide and conquer, right? Again, even if we want to use quantum computer to try to attack, we need maybe millions or maybe hundreds or thousands of qubits. So that if we want to use it, one binary variables for one qubit for one binary variable, for example. Okay, so we are still far from this, right? So, okay, how to address this? So first, I will introduce briefly about combinatorial optimization, relaxation, and then what we call quantum optimizations. Okay, this really dated back. This is like, I call it like start from a qubit, right? And interestingly, what I'm going to talk about random access code and how I use qubit for encoding binary variables actually goes back to Wissner conjugate coding. And he was a student of Columbia University 60 years ago when he proposed this concept. And like he was aware that bit can be only 0 and 1, and qubit actually, there are ways to encode more variation of 0 and 1. Instead of 0 and 1, and so plus and minus. And he was also aware that its quantum qubit state cannot be cloned, cannot be copied. And in fact, he proposed quantum money, where, for example, a bank will have randomly generated classical bits and store it and then publish a quantum money where you have this quantum state as a signature there. When somebody wants to verify this quantum money, they can go to the bank and the bank can check with their classical bit string if this a measurement aligned with 0 or 1 or plus and minus. But his paper was rejected because it was too advanced at that time, right? Yeah, that's one thing, right? So, and then actually this one qubit primitives used by Bennett and Brassard BB84, like for key distributions, also mentioned by the previous talk. But really, when we look at the power of qubit, it's kind of disappointing because even if this qubit can be used in many different bases, like 0 and 1 or plus or minus, in 1973, Holefov proved that if you want to encode 1 bit of information, you really need 1 qubit. There's no advantage there, right? So, however, before 2 years or several years before 2000, there's a new insight that if we allow some error, so here, M is the number of qubit, and N is the information and bits of information, and you allow error, a success probability P, right? Then you can probably have a lower number of qubits to encode the information. And this is the bound there. I think one of them was published by Ashwin Nayak in 1998. So if we allow error or noise, actually there is some quantum advantage. Even classical bit allowing error cannot achieve this. And of course, this is like what I did in early 2000. We proved that even if we allow some unbounded error, like where the success probability is very close to half, so almost random coin toss, there are still quantum advantages there that we can achieve by this primitive called random access code. And this, like in early 2000, we worked mostly on the theory. And recently, because we have quantum device at the bottom, we use this primitive for optimization. There are some details there, but I'll try not to touch about it. But the point that I want to stress is like early 2020, we tested this algorithm on quantum device, and we could solve with less number of qubits. At that time, it was 15 qubits. We could solve, like, let's say 40 nodes, max cut on 40 nodes, graph with 40 nodes, and so on. And we can even run it with classical simulators and so on. Okay, So what I mean by this quantum optimization, right? So of course, our hope is to use quantum computers to solve optimization problem efficiently. And usually, like, okay, this NP hard problem, but of course, well, computer science has some answer to that probably we cannot solve it with polynomial time, because we can solve NP hard problem with BQP, which is the class of problem solvable with quantum computers, then polynomial hierarchy collapse. And this is like something that's unlikely to happen, right? But I believe like quantum computer is heuristic machine. It can produce random numbers. And we do know that some heuristic, even the traveling salesman problem that I showed you before, people know it's NP hard, but somehow we can manage to solve it to billions of cities, right? So we should try to use it, even some theoretically it's hard. So what kind of advantage we can use, of course, in this space or time or approximation ratio and things like that. And people have been developing it from early 2000, for example, with this quantum annealing or adiabatic quantum computations. And there are variants of that, like digitized quantum computers, or what we call it, variational quantum algorithms in terms of variational quantum eigensolver, or QAOA, this quantum approximate optimization algorithm here, right? And our approach is what we call quantum relaxation. It's actually trying to relax this QAOA, which I will explain in detail later, which we call quantum random access optimization. Yes.
I heard that there's also quantum-inspired classical algorithm.
Yes.
For QAOA that work at least as well as the quantum version. So what does that fit in the future?
Well, actually, I can show you later. I will present you. This is actually, we have a GitHub code for that. So this QRAO, it's based on this quantum algorithm, but you can run this on CPU or GPU. And well, in that sense, we call it quantum inspired algorithms, right? Even, yeah, I'll show you, there's some efficiencies there, but of course, relative to what we compare, right? So the time scale, the scaling of this problem with the scaling of your problem size, so the number of nodes, seems to be comparable to the best classical solver. And we haven't done with GPU implementation, but even with CPU, it's already about the same. But of course, as I said, like classical algorithm has many heuristics, they have tabu search, iterative local search, and things like that. When they combine, they can be very fast and very good. At some point, we are trying to have generic one, which cannot address this. But yes, so what I say this quantum inspired to me is like we can design a quantum, revisit a classical solution optimization problem formulated with quantum algorithms and try to, let's say, compile these quantum procedures by using classical, maybe spending exponential resource, but still in this manageable size of instant, maybe we can still run it, right? Yeah, thank you. Yeah, so yeah, basically, yeah, I'll also present some experimental result later. But again, to get into combinatorial optimization problem, let's introduce a very simple example of max cut problem. So the problem is, given a graph, here is a triangle graph. There are 3 nodes, x1, x2, x3, and there are 3 edges there connecting any 2 nodes in the graph. And my task is to cut the edge of this graph so that the number of edges is maximized. And the way to cut it is like I have to label the nodes in either to be 0 or to 0 and 1. And the cut is included in the counting if it connects 2 nodes with different labels. So this is the way I can write it as an integer linear programming. So I'm maximizing the sum of my edge here for every edge. And this edge, if either one of them are 1 and the other is 0, then you can see that the value of the edge is at most 1. If both of them are 0 or 1, then EIJ will be 0. This NP hard problem. So basically, classical problem will try to, essentially will try all possible combination of 0 and 1, right? And you can see that the optimal value is 2 here. you plug in there, because in the triangle, you can only cut at most 2, but cannot be 3, right? And linear programming relaxation say that instead of thinking about 0 and 1, just relax this variable, that all variables that appear there, instead of 0 or 1, discrete one, just make them continuous between 0 and 1, and then solve it. Now there's a problem. When you do this LP relaxation, of course, you search for larger problem, which means like your optimization problem can be larger than the real one, right? So here, for example, if I make it continuous, I can make xi and all xi to be 1/2. And you see that eij will be exactly at most 1. So that the optimal value will always the number of edges, right? So if I relax this, I get the linear programming will integer linear programming relaxation will give me 3, while the actual value is 2, right? And that holds for any graph, right? But of course, linear programming, you can introduce other inequality here, even with this relaxation called triangle inequality, saying that if you have a triangle, you can only get at most 2, which is true. And there's also this triangle inequality saying that, well, the distance between 1 to 3 is at most at 1, 2, and 2, 3. And it holds, if you plug this, then this linear programming relaxation with continuous value will give you 2, the true value optimal, and also this exact solution that how you cut this triangle graph. So it's so we can relax the variable from a binary variable to continuous one. Then we can introduce inequalities, new inequalities to make the relaxation tighter. Okay, in physics, well, instead of doing this 0 and 1, we can think of this problem as labeling the nodes in 1 or -1. It's still binaries, but different representation, and the objective value you can write it this one. I think this is more familiar to researchers in physics here. So if you see here, the nodes is labeled as 1 or -1, the same label, and then this will be 1, it will be 0. It's different level, then will be 2 halves, then you get 1. So you count edge with connect 2 nodes with different label 1 or -1, where Zij square now is 1, right? So this is what we see usually for Max-Cut with Ising spin glass models. Now, here it's come interesting part. So the one way of doing this, instead of this linear programming relaxation, we can also do this in considering this variable as instead of 1-dimensional, more to lift them to higher dimensional, let's say 2-dimensional. So you represent each node of the graph as a 2-dimensional vector in a unit circle, because you have this condition that their norm should be 1. So it's a vector, the vector norm is 1, so unit circle. So this optimization problem means that you try to assign 3 points on a unit circle and as far as possible. And you can think of that you place them in the location that is far away by 120 degrees, right? Far away part. And that's the solution to this optimization problem when you assign the node as a vector in 2 dimensions. Now this comes interesting part, which I think analogous to quantum computing. You don't decide what's the value of the binary variable. When you project it to binary, it's either 1 or -1. It's just a 2-dimensional vector there. How to decide it 1 and -1? Do random projections, right? So with random projections, you force it either this the vector that is either above the plane or below the plane. When it's above, it's 1. It's below, it's -1, for example. Now what happened is, like, by doing this random projection, you got cut exactly 2, right? So without adding this inequality, you relax your variables, your decisions into higher dimensions, and then doing random projections. It's kind of like in quantum, like, unless you do measurement and you project, then you know what's the state of it. It's look like that in the optimization problem, which I find very interesting. And we got exact solution, which is 2, right? Okay, However, in this variational quantum eigensolver or QAOA that proposed about 10 years ago, that doing it, for me, it's like a direct method. For example, consider this bipartite graph with, we try to find the maximum cut of 1, 2, 3, the 6 nodes there. It's bipartite, of course, the optimal way is just cut there in the middle. So 1, 2, 3 will label 1, and 4, 5, 6 will be labeled -1. And that's optimal, right? And the way to do this, if I write this as this combinatorial optimization problem in this QUBO, quadratic unconstrained binary optimization problem, I can design a Hamiltonian, which by just rewriting all this xi binary variable xi xj into this zi szj, which is like a huge matrix, 2 to the power of n times 2 to the power of n matrix, and z is a diagonal matrix of 1 and -1 here, and the notation of z to the power I is like this chronicle product, all of them, and except the allocation is z, right? And well, this, you can write it this Hamiltonian, and it's a huge matrix. And for example, for this bipartite graph, this is how I write it. So this Hamiltonian here, it's identity. There's a summation of this two value, which actually I can infer, I can easily transform for my QUBO formulation. But notice here, I need 6 qubits. So because for each variables, for my decision variable, I need 1 qubit for that, right? And it seems the solution that I have is like one binary variable of my decision variable is encoded in single qubit by this Pauli Z operator. And if you work out this diagonal Hamiltonian, there's some maximization. The maximal one will be on the diagonal side. And you see that the eigenstate, which is the eigenvector, the ground state, the eigenvector with the lowest eigenvalue, or the maximum eigenvalue, will be like the first 3 bits are zeros, the last one are 1, or the flip of that, right? So it gives me the optimal solution of 9, right? So this is when I compute this with either quantum device or any classical simulation, I will get into this ground state, which is completely classical binary bits, right? And it will have scalability problem because if you do this, we encode 1 bit with 1 qubit, you want to say have a max cut on 1 million of nodes on the graph, we need 1 million qubits. But remember, a qubit is a 3-dimensional ball, right? So it should be more space to do this. And there's also another problem with QAOA, which I think quite interesting. For example, people have using this quantum circuits we call QAOA with alternating layer of mixer and cos Hamiltonian. So that will compute from the all 0 input states. And if you run it long enough with quite enough layer, at the end, you will get the solutions. Then how it proceeds, like you can see at the entanglement of the quantum state you produce at each layer. And there's a paper before that says that this QAOA has this entanglement barrier. It means like we start from all 0 state, just really classical, no entanglement at all. So it's like, and then it computes into very high entangled regime, like entangling all the qubits. So there's some entanglement there, all entangled qubits somehow, but it's again unentangles them to get the classical solution because the solution is classical. So to me, it's like kind of like our goal is not high, but then we go up to the hill and then we downhill again to get a solution. Kind of like why spending that in that direction, right? We actually confirm them run the QAOA, right? So there are some 2-layer, 3-layer, 4-layer, up to 8-layer of QAOA. So we run this, and after somehow it peaks and then it goes down because we have to find this classical solution that encode our the solution of our problem, right? So it's kind of like seems to be wasting resource, but of course this is the power of quantum computing. Even if you think of Grover search, it start from classical solution, go to untangle one, and then disentangle again to find the solution, which is also classical, right? So maybe it's unavoidable, but again, to have this high entanglement quantum might be very hard, right? Okay, this is my view, right? So classical optimization will start from initial state. We'll just explore classical space and get the classical solution directly without going to the uphill, like the VQE or QAA, right? So why not having a quantum optimization that start from classical state, goes to quantum non-classical state, like entanglement state, but just stays there. And then when you want to extract the solution, you perform some rounding and get the classical solution, right? Instead of untangling them. Because this is actually what I showed you before with the classical problem. Like they lift this to vector, they don't decide 1 and -1, but when you do random projection, you decide it 1 and -1, you get the solution. This is a kind of thing that we want to achieve, right? So it's actually, there's also interesting observation several years ago that probably entanglement doesn't help in optimization. That's their argument, but this is like really limited experiment. Like at that time, it was variational quantum circuit was kind of like promising. People try to look, okay, let's try to solve optimization problem using entanglement. Does it help or not? The conclusion is kind of like, oh, maybe it doesn't help at all, because even without entanglement, we still can achieve this. But when, for example, here, Control Z introduce entanglement, but when you don't introduce Control Z, it seems to be also similar to using that. So why going uphill and then downhill again instead of this, right? So if you look at this, why we might be able to use quantum state in the non-classical way is by using how we use relaxation of the bit and qubit, right? So before I show you, we relax the binary variable between 0 and 1, since we have this probability between 0 and 1, right? These variables. So we relax them. Instead of fixing them 0 and 1, we think of them probability between 0 and 1. In quantum state, quantum bit, we have this 3-dimension representation of a qubit called like block ball. And you see like the 0 and 1 actually corresponds to this North Pole and South Pole, right? But if you see it's 3-dimensional ball, there's nothing special about North Pole and South Pole. You can get 0 and 1 in the X basis, on the Y basis, or any basis you want. So there are infinite ways to represent 0 and 1. Instead, any point on this block sphere, this unit ball, you can write it in this density matrix representation in this quantum bit. And yeah, of course, like 0, 1 in the Z basis, which we think of computational basis, you can write it this one. But there are many other ways in X basis, Y basis, that here. But many ways to represent 0 and 1. Why particularly have on the Z basis, right? So to look at this, let's get back to the bipartite graph I showed you before, like this one. So the idea is here. Instead of using only Pauli Z, as I mentioned before, it's diagonal, and then you construct this Hamiltonian. I'll tell you later how to do this. We can just replace it with X, Y, some rules to do this. So we have this using this Hamiltonian. This value 3, I can explain it later why it's 3, but we can consider this Hamiltonian instead of the Hamiltonian that we considered before with the direct method. And here, as you can see, we have graph with 6 nodes, but only 2 qubits are used for this Hamiltonian. Here, X is the Pauli X, or 1, 2, the subscript here is for the number, the qubit number. So you see that we only use 2 qubits, and then we can represent a Hamiltonian where there actually basically I encode 3 binary variables, my decision variables, into a qubit. And it's based on this random access code that I will introduce later. But basically, instead of only considering North Pole and South Pole in the Z operator, we can consider X and Y also, right? And we can look at this, what is the ground state of this Hamiltonian, of 2-qubit Hamiltonian? Now what happened is the ground state is a Bell state, just completely entanglement. So there's no way classical can have this quantum state. So it's purely quantum state. So the ground state which we want to achieve is actually a Bell state. And now I can show you later, we can actually extract the solution from this Bell state of the max cut that I have now. So because, basically what it says, like the first qubit and the second qubit must be anti-correlated. If it's 0, the other must be 1, but it also means that if all 1, 2, 3 are zeros, 4, 5, 6 should be 1 or the other way. So the Bell state actually correctly encodes the solution of this bipartite graph, and it's completely quantum state using only 2 qubits. So we save the resource of qubit here, right? Yeah, so this is really what I mean by quantum relaxation. So we start from classical state, we evolve this classical state into a quantum state. We might achieve classical soon, but mostly because it's non-diagonal Hamiltonian will be the optimal solution will be genuinely quantum state. But now, of course, there is a problem how to get the solution from this quantum state, because it's not clear. As I think previous speaker mentioned about tomography, of course, we can do tomography. We can specify all of them, then we get the full description, but that can be expensive because it can span exponential number of resources. I'll show you that we can do it efficiently. Okay, so here we compress the solution into less number of qubits. And good thing about it, because it's relaxation, it means like if the true optimal value in the integer is this max cut value, in relaxation you can go beyond that max cut value. Of course, the optimal one here is the red one, but you don't need to reach the true optimal. You just need to go over the integer value, and then you relax it, and you get some theoretical bound on the quality of your solution, which we found it's still very close to half, like 0.55 and 0.625 by some, according to the number of variables you put in a qubit. The more variables you put in a qubit, the worse the guarantee you get, but that's the price that you have to pay. But if you, but still we have better than half. It's just like non-trivial. Okay, so of course, finding the true eigenstate is the QMA hard, which is like very harder problem than NP hard. But we might not be able to do that, but we don't need to find the true maximum. We just need to find something better than this integer max cut value. And this, because this ratio can be controlled by the number of binary variables we encode in qubit. Okay, thank you.
Maybe I'm not following precisely the definition of the fact. So from basic counting arguments, right? Say in smaller space, you're not saying the usual way calculating all the two and normal solutions. How is the relaxation? How do you guarantee the ground states in that manifold is called it?
Oh, okay. So when I do this, I can introduce it. So for example, I have a Hamiltonian, and then I can show that this, if I encode binary variables as a product state of this n qubit, I can guarantee that it encode the cut solution. So I always know that. No, it's not, because the encoding, for example, this construction, it's polynomial. You can find this, for example, how you encode this x1. I'll explain it later, but that you can do efficiently. I mean, almost. Yeah, again, this like how, if I understand your question correctly, like how can I construct this Hamiltonian, right? H is a thing. N to power n over n divided by 3 to the power n over divided by 3. That's just closer, but yes, kind of like, of course, but then I encoded this solution not in the orthogonal one. When before it's all binary string as orthogonal state, here is non-orthogonal state. That's why I have smaller number of space. Right? Yeah. Okay. Oh, okay. Maybe like, for example, here I use 1 qubit to encode 8 states, right? But they are not orthogonal.
So 8 bits, whatever, 2 bits, and you got to round, let's say, back to your three solutions.
Yeah, yeah.
We got a question, but I'm sure we'll be
okay, okay, okay. Then I hope I can answer it later. Yeah. So yeah, basically this is what I mean resembles what Goman-Williamson, which is like the best classical algorithm, generic classical algorithm for max cut, like do SDP relaxation that I showed you before, do hyperplane rounding, percent ratio is optimal under unique game conjecture. But again, this, that's the idea precisely, but that the vector will be higher dimensions, the random projection still like that. But again, this is the way it does. And of course, if there's some graph with small gain, which is like if the cut is slightly better than half plus epsilon, then Gummel-Lensam might be worse than random guessing because it can be the guarantee is less than half. It's not trivial, worse than trivial lower bound. In our case, if we can find ground state whose value is better than classical cut value, integer cut value, then we actually have guarantee, but still better than half, which probably for some region might be interesting. It depends on the number of variables that we have. Okay, so what I do is to use this a primitive called quantum random access code, and I would like to introduce that. And yeah, okay, how we can encode a qubit for encoding more bits. So this illustration problem of let's say Voyager reached a solar system with several outer solar system several years ago, I believe. Still working. It sent us some signal, but that radio signal will travel about 23 hours before reaching us, right? And let's say it wants to send us a 2-bit of information. Is it malfunction or other has reached outer solar system? Something yes, no. But the Earth, of course, didn't tell which one it wants. So then can Voyager send 1 qubit to the Earth so that the Earth can know either one of them or both of them, for example? Then how many bits Voyager has to send? Of course, if it's without error, Hollefaux bound dictate that we need to send 2 bits or 2 qubits even. So there's no saving in the qubits. But of course, if Earth only wants to know 1 out of m bits with success probability p, which is like, let's say 0.7 or something like that, then we can bound it. And actually we can do it with error. So, but of course the bound doesn't forbid us to send 1 of 3, 1 of 4, something like that. So if we tolerate some error. So there are ways to use a qubit to send more bits of information on the status of Voyager, right? And how it does it by using a qubit in this form. So it places 4 points here in the on the corner of this black ball. So if you see it's 2-dimensional here. So here's like it's B1 is by either 0 or 1. So this coefficient of this quantum state and mixed density metric representation here, and B2 here, it's a Pauli Y, and this Earth will measure it with applying this measure in the X basis on the Y basis and get this bias towards the solution of the answer to B1 or B2 here, right? So there are ways to put 4 points on the block ball so that depending on what the Earth wants to know, it can know the value of either one of malfunction or the outer solar system. But once the Earth did it, it forget the other informations. So it's kind of oblivious transfer, but yeah, there are ways to encode this in this fashion. And I say this like a problem of slicing pizza into 4 pieces because basically what it does is there are 4 points, you put each point in the quadrant and you try to cut the pizza into by 2 measurements. 1 and measurement 2 is like taking the first bit, measurement 2 is taking the second bit, and then by cutting a pizza 2 times, you get 4 pieces of pizza. And that's the idea, actually the proof idea, you can do this and encode 2 variables into 1 qubit with this success probability. And of course, by the same argument, you can also show that you can also encode it 1 out of 3 binary variables by 1 qubit by sending this type of information. So encoding the answer to the binary one in the X basis, Y basis, or Z basis, and the Earth can choose either to measure in the X, Y, Z to get the bias to the solution, to the answer that it wants, right? So basically, it puts the 8th state, which corresponds to the all 0 to all 1 value at the corner of the block ball in this cube like this one, and this one will give you. And this is actually, you can also play with Qiskit to see how it works and even the quantum device. So basically it's like, this is the graphic representation of how you present 3 bits of information into a qubit. And actually we can say that geometrically, a measurement is a hyperplane cuttings, and quantum state is a point on this block ball. And we can also do this argument on the higher dimension. And it's also bad news because it also means that you can not encode 4 bits of information in 1 qubit, because there are no way you can cut a cake into 16 pieces by 4 cuts. You can try it. So this the 3 is the limits to this. Basically, even if you allow a probability, worst case probability with slightly better than half, there's no way to do this geometrically. That's 8. That's why it's 8, because 4 is like I mentioned pizza, right? But of course you cannot cut pizza horizontally, so I have to use cake. And then 4, and then you cut horizontally, you got 8. But then you cannot go 16 by another cut. There are no ways to do this. Yeah. And you can go to higher argument. So this is, so one of 3, 3 bits is the most one in 1 qubit. But if you go to 2 qubit, you can encode 15. You can go to 3 qubit, you can 4 to the power of m-1. So this is what we proved before. And yeah, so this is basically really like geometrical arguments. Okay, this is the definition of quantum random access code. So Alice has n bits of information. If Bob wants all of them, Hohlefeld bound forbid it. But if you only want one of n bit, again, Hohlefeld bound still holds. But if it allows error, let's say it's okay to succeed probability larger than half, then this is like random access code, like using n, sending n bits of information with m qubits, so that any one out of n can be extracted with probability at least half, well, at least p, larger than half. No entanglement, no third entanglement, no third randomness. And this primitive or random access code has been used in automata, information theory, locally decodable code, private information retrieval, even random number, and so on. So I think like Mark maybe knows about this more. Yeah, so basically, but surprisingly, not so many known about these constructions of random access code. For example, 1 qubit, it's a ball. It's very easy to imagine it. It's I've shown you before. That's optimal. So like 2-1, 3-1, the probability we know is optimal. 2 qubit, not so many known. Even like I did this with numerical before with using standard semi-definite programming. We know you can encode 3 bits into 2 qubit with this success probability 5 and things, for example, and 7, 8, 9. Of course, there's generic construction, but we don't know the probability is optimal or not. Even when using encoding 7 bits into 2 qubit, we can only use mixed state. There's nothing, probably you cannot use pure state, for example. There are some ways to do that, but geometry become very complicated and not so many known for other qubits. So this is something up to date to now. And actually, like, what's the connection? It's like, okay, it's kind of going to it. Theory, it has connection with mutually unbiased basis. But actually, we need larger definition, we call mutually unbiased projective value measurements. And we saw that the existent or non-existent this random access code correlate to this mutually unbiased projective value measurement. And we have theorems about the existent and non-existent connecting them, but this is not relevant for this presentation. But what I'm going to do is like how to use this random access code for quantum relaxation. And then we got our quantum random access optimization, or QRAO. Okay, so this is to explain it, I will go to explain first the QAOA because they're popular, and I think they're still one of the best quantum algorithm at the moment. So we are given the QO formulation of our optimization problem, written in this with Zi and Sj's binary variables. For each H, we want to maximize the cut. And of course, the first part is constant, so we can think of minimization, ground states, right? Then Xi is also this notation. And this is like, there's a mixer Hamiltonian. Basically, it means like we create a state which has overlap with our solution, right? And the cos Hamiltonian is designed from this objective function that we want to minimize by just replacing this value with this matrix and sum them to Hamiltonian. Right? This is in the QAOA. And the QAOA will define this, what they call quantum alternating operator ansatz. So basically, you prepare the initial state. There's a layer here where the gates here depends on this cos Hamiltonian here. And the next gate here depends on this mixer Hamiltonian. And then you alternate this layer up to the depth you want, right? And then we repeat it. But again, there's a parameter here called gamma and beta for each cos Hamiltonian at each layer. And that parameter, if optimized, you will get the optimal value, the solution here. Right? So the quantum state will be evolved by this quantum circuit. At the end, you have this psi p which encode the solution. And you can measure this in computational basis and give you the bit string 0 and 1, or that give the solution of the max cut problem. Right? So this is the QAOA. Then what happened with our random access optimization? It starts from the similar optimization problem, binary optimization problem with n variables. We have this mixer Hamiltonian. We can use also Z here. But okay, what's the non-diagonal cos Hamiltonian? So here, as I showed you before, we use Pauli. We don't restrict ourselves to only Z, but only use X and Y. And there are 3 types of them for each qubit. We somehow construct them. I'll explain the construction later. Assume that we construct them here. So it's still weighted to non-identity Hamiltonian here, the sum of them. And then how to define the circuit for this QAOA, or quantum alternating operator ansatz here. Well, you can do this also similarly. So there's a way to do this by trotterization or group trotterization and so on, and evolve them. And of course, we can also use the parameters by the QAOA and get the quantum state. But now what happens, I think previously also asked, now we have n over 3 qubits because we encode 3 binary variables into 1 qubit. So the number of qubits only 1/3 of the original number of variables. Then we have to get the solution, right? So here, the measuring state in the Z basis alone will not suffice. We have to do more measurements on the other basis. Okay, how to do that? Okay, before that, this is like what we did in at my company now, that we saw that actually by applying this parameter schedule that people has been doing at QAOA with this direct optimization, we can get similar result. We can bet as we extend the length of the QAOA circuit, we get better approximation ratio. With some rounding there, we make it solution worse. We save 3 times the number of qubits. But of course, if we do QAOA without error, QAOA wins. So if fully optimized QAOA solutions are better, but the message is here, any techniques at optimization of QAOA, we can also use it for quantum relaxation. And indeed, this is what I think very intriguing. So if we do direct optimization 1 qubit for 1 variable with QAOA or diagonal Hamiltonian, and this is like we use a small graph of 14 nodes, and we repeat this optimization over 100 trials. If we find the true ground state, so m equal 1 is QAOA, right? So you always get true optimal by QA. Okay, you get with probability 1 optimality, nothing else. But we encode more variables into a qubit, let's say 2 variables or 3 variables by random access code. Sometimes you get lower than the true optimal. So there's some error here, but most of the time you still get true optimal. But of course, in this case means like QA is good. So if we can really truly optimize our quantum circuit, QA is better. But what happens if we have limited number of entanglements? We cannot go into the truly optimal. Now things get interesting because QAOA, for example, with this limited, I did this with matrix product simulator, MPS, with bond dimension limited to 2, for example. QA can only give, well, of course, small probability it can get to true optimal, but mostly get about 8 or 9 here, like this one, after 100 trial average. But for the relaxation, even if you don't get with limited entanglement, the majority probability still get to 12 here. So if our circuit has error or limited capabilities, probably relaxations is promising based on this small experiment, right? Okay, so we want to do this random access optimization with Hamiltonian. The challenge now is like how to define the non-diagonal cos Hamiltonian there that only use n over 3 qubits, so 1/3 of the qubits. Then how to do this? Again, our inspiration is from this QAA, from the Ising Hamiltonian. Let's assume this Peterson graph, which has 10 nodes here, right? It will use this Z basis as these encoding binary variable. So you see that Z here with the subscript for the where you put the qubit. So this node is put in the first qubit, this node in the second qubit, and so on. So we'll use 10 qubits. So this is the Hamiltonian, right? Now, given this quantum state, which is computational basis, like the first one is 1, the rest are 0. This is the quantum state representing it. We can confirm that this value is the cut when you assign the first one to 1 and the rest to 0. So this value and the cost function of this, again, this quantum state is the cut exactly encoding this classical solutions, right? So when we do this maximization over all the possible quantum state, what we will get is this binary string that maximizes the cut, right? So basically what this QAA is like, there's a quantum state here. The optimal will happen at the binary string that encode, the quantum state that encode the binary string for the max cut, and that the true optimal, and that's the optimal for the quantum space that you have. In our case, for the non-diagonal encoding strategy, we'll use this X and Y also. Here with the analogy, if it's, you see that if there is an H, I, and J here, they're on the different qubit. So we have also to do this with this non-diagonal. So if there are H between, let's say, this nodes, it has to be on different qubits. So to do this, we first have to color the graph so that any node connected by an H have different colors. And then nodes with the same color can be put in the same qubit. So this is like how to do this. So the subscript will be the location of the qubit, and then we can assign X, Y, Z, like this one. And based on this graph, we can construct this Hamiltonian. And the 3 here is based on this random access code, but we can forget about this because we can do minimization, and the constant 3 is not important here. So yeah, again, so the idea is like color the graph that you want to cut with maximal cuts, then assign this node on the same with the same color on the same qubit, and then build this construction Hamiltonian based on this coloring. And we can confirm ourselves if we have a quantum state, which is a product state of the random access code that I've showed you before for 3 bits, then any product state of this 3 bits of encoding, it will encode the cut value of this graph for any possible bit string that we have, right? So now we are going to optimize over all this quantum state, but of course our quantum states are larger because we have entangled quantum state that need not be product of this QRAC state, so we have larger value. So we can have value, this objective value will be larger than the true max cut value, where we have to do rounding there, right? Is it something? Is there any questions so far? Yeah. Yeah, so now it comes like we got a quantum state with a certain number of qubits. Now, how I extract n-bit string from 1/3 of the qubits, right? So this is something that I have to explain for describing this random access optimization. So of course, like we got this quantum state on this, for example, on the red one, and the quantum state that optimized this non-diagonal Hamiltonian that encode my optimism problem will be entangled, or maybe some quantum state here with the number of qubits is 1/3 of the n. And one way to do is like just as we did with this random access code, like for each qubit, we observe in the X, Y basis, and based on this bias, we round it either is 1 or -1, because for each of them is X, Y, Z. So assume that they're close to the product state or product state of QROC state, we actually can extract the bias here is either -1 or 1 by measuring each qubit in X, Y, Z base and just repeat it 3 times. And because it has error, we have to repeat it many times. But because we have the circuits, we can have copies of this quantum state as many as we want, right? So for each qubit, instead of measuring only in the Z basis, we can measure in the X, Y, and Z. So 3 times of n/3. So we extract n-bit string from this. That's one strategy to get the Pauli rounding. The second one, we can do what we call magic rounding. So this is, in the Pauli rounding, it can be very bad. It's very highly entangled because entanglement actually destroys the solutions. But for magic rounding, it has properties like it's a random projection that actually make it looks like the polarizing channel. So still preserve this quantum state if you do it randomly. And by this rounding, actually, we can guarantee that if we go better than these integer solutions, if we round it with magic rounding, we get guaranteed that optimality better than half, which is trivial, which is 5/9 for 9. It depends on the random score. We have some theoretical guarantee of the quality of solution by this magic rounding. I'll not go into detail, but there are ways to extract this. And yeah, this is like the way of magic rounding doing is like what people call it like symmetrically information complete POVM, but I will not go into details into this. But basically, like we have a table that saying that based on the compression ratio, how many variables you put into a qubit, based on known random access qubit contrast for 1 qubit, if we have put 2 variables into 1 qubit, and then the approximation ratio will be 0.625, or if it's 3 bits into 1 qubit, 0.555. It depends on the success probability of random access code. So there is a trade-off between the error you got from random access code with the approximation ratio in the combinatorial optimization. And of course, this question about how we can encode more. And in fact, if we use we use 2 qubits to encode 3 bits of information with this random access code that we found. The success probability is 0.9 something, and the approximation ratio becomes larger, 0.7 something. So we have some conjecture that will be approximation ratio will be like this form, but we don't have many construction of random access code, so we need more research on this random access code. But yeah, this is something that, sorry. Yes.
I understand you have a wave encoding by that. I understand you have wave of rounding to get to the 3/4 now by that. I'm not following what you do in the middle. You map your depressant point and then there's some by the way.
I'll go into that. Next. Nice. Yeah, of course. Okay. Good question. Actually, like, I haven't shown this, right? How we do this, right? Yeah. So, of course, it's basically, okay, that's like, okay, that's go here. Okay, that's experimental. Okay, this is what we did. Of course, at that time, we didn't know QAA, how to do this, but of course, we can do variational, right? So, yes, the cost function there, it's variational circuits, right? We just like the straightforward to do this and just the parameter of that. So because like QA parameter is kind of like still ongoing research. As I mentioned, we did that. We confirmed that we can use the scheduling in QA, the diagonal one. For the non-diagonal, it seems to work, but we need more. Yeah, I hope we publish papers on that. But basically, first we did this variationally, like because you can do it with near-term quantum device, and just do that. And yeah, actually we experimented with GPU. That was my student at the University of Tokyo before. What we wanted to do is like to see what happened without entanglement and with entanglement. Which means like if we repeat it 0 times or we repeat this entanglement 1 time and 2 times, like how the solution changed for many different type of graph. Graph can be unweighted, weighted with plus and minus 1. And remember that Gumbel-Williamson doesn't work with minus weight. So we don't know. So there are ways to do this kind of, and this is like the example of the graph that we did. This how entanglement type that we considered is something like that. Yeah, but then basically like we always can have solution that larger than the integer solution. So even for product state without entanglement. even without entanglement, sometimes we also get better, so like very close to 1 here, approximation ratio. And this Pauli rounding that I mentioned to you, just measure each qubit with X, Y, Z, because entanglement can be really bad. It really give you even smaller than half at the worst case. So no theoretical guarantee. But here, for example, we don't see really proof that entanglement help, because it seems to be like more entanglement here doesn't improve the approximation ratio. Pauli rounding seems very bad for graph with 48 nodes. But there are instances where actually having entanglement, where without entanglement, you couldn't find the optimal solution. With 1 entanglement, you get optimal solution, also with 2 entanglements. So it depends on instance. This is 1 instance on 46 nodes. We can like do average on many graphs. It seems to be like having entanglement help us to improve the number of graphs that we can find optimal solution. Yeah, but really this is something that depend on the graph instance, right? Yeah, so basically entanglement is kind of like complicated. Sometimes it helps, sometimes it's not, but we argue that it might help. But here with our learning is like Pauli rounding seems to be not good, but in experiment, no theoretical arguments guarantees, so it's not good, but experimentally it seems to be better. So our kind of thing, like maybe too much entanglement is not good. Maybe you should stick with less entanglement, right? So how to do this? Actually, okay, I'll go into this recursive. So we develop a new one called recursive quantum relaxation, and we have the code for that. And yeah, so basically in the recursive one, so what happened with QA, the hardest part is like how to design this parameter for this each layer, right? So this is kind of still ongoing research, and it seems like you need the number of depth, the layer is like poly or linear in the number of qubits, because you have to entangle all the qubits. So by the light code argument that's shown before, then we need like a very deep quantum circuits, right? To entangle all the qubits from 0 to the end of the qubit. Right? So it's kind of hard. And how to avoid it? It's Sergey Bravy and others, like they came out with this idea of recursive one. So instead of doing this full optimizing like very deep circuits, just consider QA with 1 layer. And this 1 layer, low entanglement, you know this classical analytics of the parameters, right? You don't need to run this. Even there is a formula to get the parameter of the optimal parameter for 1 layer. And basically what it does is like have a graph G, and this graph, you compute the optimal quantum state with 1 layer of QA, run it, and because you know the optimal parameters, now get the edge of the graph with certainty, which means like with the highest value here. So only 1 edge there, get 1 edge, and if the value of this edge contribute to most of the energy that you want to minimize, the absolute value is like the largest one, and then you don't decide the assignment of the node either 1 or -1, just whole of that, get the parity is either they are on the same side or different side, either the same label or different label, but don't decide it. Just get the most contributing edge and remove 1 of the nodes. And then modify the graph. And then by removing 1 node, you have 1 less number of qubits, a smaller problem. And then you repeat this iteratively, right? Until you get small enough that you can do brute force. So it's very nice idea. So 1 layer is usually like you cannot do fully entanglement, but by doing this, removing the node, 1 layer, and then you merge the node, it means like you can do non-local operation by this merging of the graph, by making the graph smaller and smaller by only using 1 layer of QA. So the idea is like this is the original graph. For example, this red and the green one is the most contributing edge. This one that you want to get the parity of this. And you, for example, if you decide to remove the red one, and then all the other node not removed connected to the red one will be rewrite to this green one. Because if let's say red and green are on the same parity, like parity is 1, so they have the same labels. So the max cut of the other value will depend on the green value and vice versa. So there are ways to reduce the graph one by one node at a time by doing this recursive QAOA, but only doing one layer of QAOA, which you know the analytical solution. And interestingly, they saw that there's instant of QAOA which constant layer, and but the original QA with constant layer cannot beat Guman-Williamson, like classical best algorithms, right? And he also demonstrate that there's instant where recursive QA beat this Guman-Williamson, the best classical. And there's also theoretical evidence lately about this recursive QA with limited number of layers. So basically, the recursive things that we have power of doing this with limited entanglement, it seems to be good. And what we did is this recursive quantum randomness optimization. So instead of doing this with one layer of QA, we did with matrix product simulator with limited bond dimension, and we have the code in PyTorch and CPU. And the idea is kind of similar to what I saw with the recursive QA. But remember, in the QA, like you have only Z, so there's no way to permute this, like all Z, only the where you put the qubit and so on. So it's not many variation. With our method Hamiltonian, remember we have XYZ, and actually you can permute this XYZ. So there are many Hamiltonians that encode your problems, different Hamiltonian with different ground states, right? So what happens, like we generate all this type of Hamiltonian and get the average of them and find the most dependent edges, and we fix disparities and just do what the recursive QA did. And we see like we have, of course, the number of qubits is smaller. We have more Hamiltonian and the entanglement is limited there. And if you're interested, the code is available on GitHub. It's actually my colleague at Toyota Research Lab coded this. And it's the paper is in the archive. And you can also compare it with the recursive QA, with Guman-Williamson's SDP relaxation. So he saw how to install it. And actually, surprisingly, the best classical is Circuit, which is like the fastest and the best one. And Circuit is kind of like sub of the Guman-Williamson because it's lifted the solution into 2 dimensions instead of the number of node dimensions. And it seems to be the fastest and find the best one. So the code is there. So if anybody is interested. And this is the experimental result. So we did experiment with graph with 800 nodes available on GSET. So GSET is kind of a standard benchmark for many optimization on graph. So here, for some of this graph, there are many other instances which we don't know the best solution, right? But this is like best known solution by, I think, breakout local search. There's some local search software there that find this is the best solution for this graph instance from G1, G6, and so on. Guman-Williamson here, you can see that it's not that good, right? But it's close to this best known. And you see like Circuit has better than Guman-Williamson most of the time. And QRAO here is like the original one without recursive that we found, that I showed you before. That's kind of like also, well, find this closer solution. The recursive QA here in this value. And this is the recursive QRAO that we found. And you look at this find, so we have 20 Hamiltonian, we average them. This is without the averaging Hamiltonian. And you see the value, compare them, seems to be better than QAOA, right? And remember, we only use 1/3 of the qubit. And even with the recursive one, we are better than the original QAOA. So, and, but of course, it's still like slower and not as good as Circuit, but very close. And how about this, when you mentioned this quantum inspired, we run this in CPU and then we can compute, for example, this one is for the computational time. So the the y-axis is the time that we run this, where here is time the number of nodes. So we run on this 1,000 nodes with 1,000 graph, I think. Yeah, up to 1,000 graph, something. And then the age is like a plus and minus 1. And you see like the red one here, we still like spend a lot of time. But if you see the growing, the scale of the computational time compared to others, it seems like we are better than QAOA, recursive QAOA, because recursive QAOA is very steep here. but we are kind of like slower. And yeah, so, and we run it on CPU. So maybe we can exploit GPU, maybe we can get it smaller. So basically, if we can implement this on classical device simulating quantum computers, because maybe we can have some quantum inspired algorithm on this, right? And this is the solution with regards to Guman-Williamson. So our solution here in red seems to be at least or the same or better than Guman-Williamson solution. And interestingly, recursive QAA seems to degrade the solution with the number of nodes, but the quantum relaxation gap seems to get better with the number of nodes. So this kind that we have. So maybe this is the end of my thoughts. So I would conclude that we believe that quantum relaxations is a tool that we're actually using noise. Well, kind of sense that, well, because we don't have perfect qubit, but it's okay that we can repeat it and then encode our solution to actually help us save quantum resource. It seems like we don't need entanglement, but limited entanglement helps. And what is interesting, like we start from QAA, and somehow we do relaxation. We use less number of qubits, but somehow we get better than QAA, at least for the experiment that we did. So maybe something theoretical analysis that we can do for that. We haven't done much on that direction. But of course, another interesting thing from this quantum information perspective is like, can we design like generic QRACs for, let's say, if you have 10 qubits, how many variables you put reliably that you can use for optimization, maybe 100, then we can scale 10 times and things like that. If we can do that, will be nice. So idea is like, even if we have noise, or we can still do something there, interestingly. Yeah, so again, this is summary that I presented before. And yeah, so we believe that QA will be, it's one of the best heuristic. We have generalizations there called quantum relaxations. And we have several nice property which you can try. And if you're interested, please, yeah, you can test our algorithm here. Yes, thank you very much for your attention.
I think most of my previous questions were answered. Thank you for your comments. My question is, normally when I think of these type of things, I think sort of betting and easier problems, like LP or something that you're going to solve with some sense, and I go back. You guys can do the opposite, like it's sort of embedding in a harder problem. And so I'm curious in comments just on that aspect, but and then the follow-on related is, because of that, I would expect a high dependence on the particular encoding. So sort of in the bipartite example, if you somehow accidentally hit your coding to sort of winds up with this tree, you sort of get a simpler quantum Hamiltonian as opposed to the general case, if you're doing comments that, and then how you expect scalability to come in.
Yeah, I agree with you. Like this is actually why the recursive one where we do this different type of Hamiltonians actually try to break the symmetry, right? As you mentioned, this bipartite graph. So honestly, I don't know how to avoid it, but of course, like at some point, if you do have Bell state, as I mentioned before, as a ground state, that actually bad news, because like when you do Pauli X, Pauli Y, Z on one of the qubit, the other qubit collapse, you got only completely mixed state, no information at all, right? So you actually want to avoid that. And somehow with use low limited entanglement, you will not reach into this completely, highly entangled, just good. So I agree with you, like how I encode this X, Y, Z, if I have a graph, like how I encode this non-diagonal so that it's easier for me to decode it. So ideally, product state is good because then you can do tomography, or I can when I project it, right? So I can get it. But yeah, at the moment, like I don't know how to do this because I think it's new. Like it's also depend on how you design. For example, one qubit, it's too obvious, only 3 times. But now you have 2 qubits, 3 qubits. Actually, our construction, if you look at the paper, we have this 3-2 using 3-2. The measurement or the Q state there, it's kind of exotic. I don't know what's the intuition behind that. And also, for example, before I told you we need this coloring, right? That means if our graph is dense, there's no way to color them so that you can save 1/3 bad news again. But actually, we avoid this. Actually, you can still save 1/2 by using tetrahedron in a qubit, and then you can guarantee that for any graph, you don't need coloring. You can always have half the qubit number. Now the Gantt approximation ratio, it's come like messy because there's some asymmetry there and so on. So yeah, still ongoing. I don't know how to do that, but yeah, there are ways, probably there are many ways to do this. But I think like my invitation for theory, like do this quantum random access code, maybe we need more theory on how to construct it efficiently. I mean, like, or definitely, I mean, in definitive way, because what I found paper by Ambanis by other before, the construction of random access for quantum random access code, they only use classical random access code in general because the saving is asymptotically constant. So they don't care about it. But of course, even constant for engineering perspective is important, right? Like 10 times is different from 100 times faster, for example. So yeah, so again, like this one, we still don't know why recursive help us. We need more experiment, of course. And some of my students also even try to do this with optimization with constraints, right? Because here is all without constraints, seems to be easier. It seems also to work, but we don't know the theory behind this. Yeah. Thank you.
I have a out there question. You mentioned that there's the relaxation method. It's really interesting concept. And you mentioned the linear programming relaxation where it goes over continuous variables. I was wondering whether that has been looked into for quantum variables. For example, when you want to zero instead of qubits and you have zero eigenvalues. And if you heard anything about things like that.
At some point, I think QAA or as it like encoding Z is also continuous, right? That actually, yes, yeah. Indivisible, yeah. Yes, yes, yes.
Whereas also define different variables inside the test.
Yeah, inside.
Mathematical state or amplitude state of the field.
I think there are, well, heuristic, I think there are many papers trying to do that also, right? So in this case, I'm kind of like also going bit, so there is an extreme like this one, 0, 1, only binary in here. There's also like this one, like continuous in this probability amplitude. I think if you see the paper, many people do this heuristically, even like trying to say that you can solve it exponentially less number of qubits for some this problem by encoding in the probability. In my case, I'm only using discrete like 8 on this qubit, right? So it's kind of like in between. So
yeah,
but,
I was wondering whether that was in you know.
Yeah, but I think like for that, it's hard to get this approximation ratio as we saw before with connects with random access code, as I showed before, right? So, but mostly, I mean, like this is in, well, people when solve a problem, they don't care about it, but either they can run it and find the solution, right? I think that also, but I think there's some theory, but I'm not really familiar with them. Yeah, thank you.
If there are more questions, it's time to speak it again.
Thank you very much.
I think one is over there.
Thank you.
Really interesting.
Yeah, you learned about that.
Okay, yeah.
You were at this lunch.
Thank you.
Okay, now I have to share. This working? Can you see my slides? On okay, can you see the slides on Zoom? I guess is the question. Okay. Please protest on Zoom if things are not happening correctly. I'm not sure. Okay, so hey, I want to thank Mark for inviting me. It's a pleasure to be here. I'm very grateful for the first two talks. I learned a lot, and that was very, very interesting for me. There's going to be a change of pace, as Mark said, because this is an experimental talk, and this is an experimental talk about the type of qubits that you guys are not familiar with. Because we're making, we want to make quantum computers with light. So I guess that's my best way to describe this is a dark horse approach. But we believe dark horses can sometimes win races. That's the expression. So this is coming from my group at the University of Virginia. And we've been funded by National Science Foundation for a number of years, from DARPA from time to time, at critical times, from Jefferson Lab in Newport News, with whom we collaborate on the matters of quantum simulation. We're trying to set up quantum simulation of nuclear physics using light. And last but not least, there's a startup company, QC82, which we co-founded with 4 colleagues at the university, and whose goal is to make photonic quantum computing hardware. So more about this, maybe I can move this out of the way, I don't know. Apparently I can. Okay, I'll leave that little green and red thing in the middle. So Joe Campbell, Andreas Beding, and Xu Yi in the Department of Electrical and Computer Engineering. I'm in the Department of Physics at the University of Virginia. We've been working on these things for a long time. So I'm going to tell you about my quantum optics experiments, which are, you know, mirrors on the table, lasers, things, and AMO kind of physics. Joe does world-class photodiodes, in particular of the avalanche kind. And he designs new materials and designs novel photodetector, such as the staircase photodiode that was invented by Federico Capasso, and Joe's group made that a few years back for the first time. Andreas is taking all of Joe's stuff and putting it on chip. So you see here optical waveguides, and there's like photodiodes and metallic pads to extract the electrons out of a photon signal. And Xu is taking basically all my experiments. So Xu was a grad student and postdoc with Kari Vahala at Caltech. So he knows optics on chip and all this. Maybe you see here little rings. These are the same thing as these optical resonators, but you know, there's a penny here, and there's gazillions of those, right? So integration begets scalability. We want to build scalable machines, and we think that putting all the quantum optics on chip is the way to do it. Of course, everything has to be good enough. No quantum hardware, I think we can say, is good enough, although progress is being made all the time. Things are getting now quantum error corrected. Eventually, they're getting over the fault tolerance threshold, and you know, we're off to the races. Why do we want to even bother when IBM is going full force into superconducting qubits? Because our stuff scales like crazy. And number 2, it's not cryogenic.
as in superconducting cryogenic. It's room temperature or near room temperature. So that's why we think, hey, might as well give this a shot. And the scalability, I will tell you more about this. So this is what my group is, photonic quantum computing. We have a lot of collaborations, in particular with Mario Dagenais at University of Maryland. Quantum simulation of nuclear physics, which I mentioned. Machine learning for quantum photonics, which is something we just started. It's like, well, machine learning works, so we just discovered that. It's not a discovery, everybody knows that. So, but we used it for our purposes of quantum state preparation for quantum computing resources with light, and it's like, oh wow, so it became a thing. And also work with other people, particularly in France at the moment, on the same thing, on integrated photonics in different regimes than what we're doing. This is the nuclear physics thing, because there was a really nice LDRD grant from Jefferson Lab with Robert Edwards, Raul Briceño, who was at Old Dominion University, moved to Berkeley. My postdoc, Carlos Gonzalez, who's now at Xanadu. Miller Eaton, who is one of my two best grad students. I can't tell the difference between the two top grad students. And George Siopsis at University of Tennessee, Knoxville. And this paper came out a week ago, finally. And it's a nice, we talk a lot about quantum sampling, circuit sampling, and there's this idea that, if you sample enough, you get a probability distribution. So there you go. But the sampling has an overhead that usually is exponential or super exponential. And in boson sampling, that's the case. But here we have, and it's a proposal initially by Steve Jordan, Lee, and Preskill about using this kind of quantum sampler to construct scattering amplitudes for quantum field theory. And they wrote that paper for qubits, and it was translated for continuous variables. I'm going to talk about the continuous variables, which is why I bothered you with some questions, because we work with optical fields and think harmonic oscillator, position, momentum. So you have the phonons, energy levels are discrete, like the photons, but the position and momentum in a harmonic oscillator are still continuous, even quantized, they're continuous variables, right? And in optics, in quantum optics, the electromagnetic field is a harmonic oscillator, fair enough, right? Oscillating plane wave. Its amplitudes are exactly like position and momentum, and they're real numbers. And we can encode quantum information in continuous variables like that. And there's at the end of the day, and that's why we don't have qubits, but at the end of the day, you still want to have qubits. And so there are ways called the Gottesman, Kitaev, Preskill states that you can encode qubits in an oscillator. And so this is the whole story. So, but because we work with fields, why not simulate fields with fields? Because hey, it saves you the pain of working with qubits, because you really don't need qubits. So we're looking at those things, and it's also I couldn't find high resolution pictures of Chris and high, so this is the best pictures I could find. It's just like annoying, but should have asked him. But these guys are doing electronics at Jefferson Lab, and they built some FPGA instruments for us to measure photons, and we could do 100 photon measurement counting, which is kind of a record and for random number generators in collaboration with Chris Gary. Okay. So I'm going to tell you why we think we want to build computers with light. So this, you're very familiar. I know you're much more familiar with this than I am, actually. But this is a quantum circuit. This is a teleportation circuit. So the circuit model is not what we use. But the circuit model, of course, of teleportation is this. And so this takes with Hadamard and CNOT and makes an entangled state, a Bell state. This is actually the reverse in a computational basis measurement. If you reverse, you measure in the Bell basis. So that's a Bell basis measurement. And then you get some results, zeros or one. And then that informs. So depending on the results, you get some extra-pauli's. But here, that initial state that was there is now here by virtue of the entanglement channel and the measurement. And eventually you do the feed forward to get rid of those pesky boundaries or not. If you want to keep them, free gates, hey, you know, and that's fine. And in fact, you can use that to make a gate. And to do that, you just rotate the measurement basis here. And you could, you know, measure in a plus minus basis instead of a 0, 1 basis or whatnot. And that rotation will get teleported to here. And so that's, okay, one way to make a gate is actually to do a teleportation and do it wrong, but on purpose, because you can control what gate, if you rotate the measurement basis, you rotate the teleported state, which is great. And in fact, people went beyond that. So that's the top right corner paper there by Gottesman and Chong, where they expressed that teleportation is, that's 1999, teleportation is a primitive to quantum computing. So you can actually make up the universal gate set for quantum computers using only teleportation. And one of the things for single qubit gates I just showed you, right? And for 2 qubits, you can also arrange that. And then that was taken one step beyond by Brigel and Rasendorf when they invented cluster states, and they showed that you can generalize. So teleportation is just a Bell state, right? The two qubit entangled state. And you do something to that one, and that one fills it and gets the state teleported to it. What they proposed is to build cluster states, which is, these are those states here. And the recipe for this is, I guess, well, you take all the qubits in the plus state and you put CZ gates between them. And the CZ gate, what it's going to do, if you expand the initial product state, it's just going to flip the sign of 1, 1. And that entangles them. That if you try to refactorize, this is what you get. You get a Bell state to a local Hadamard on either one of the qubits. And the cool thing about this is like now you can make up a square grid lattice of entangled qubits using that recipe. All the CZ gates commute with each other, so it doesn't matter which one you apply, which order, it doesn't matter. Once you have that, just using measurement on a single qubit and feed forward, like, you know, the teleportation thing when I remove the X and Z's by using the measurement results, that's called the feed forward. If I have just single qubit measurements and feed forward to the neighbors on the graph, I can do all the universal gate set. So it's a universal quantum computing, it's called one-way quantum computing, so it's 2001, by Robert Rasendorf, when he was a grad student. And then basically when you have that thing, that's from their paper, you had initially that square grid entangled state there, and you do, this is our spin measurements out of a plane that disentangle, or in the plane that actually teleport. And you can do, and these are like spins at an angle here. These are non-Cliffords. Right, so you have a SZ, SX measurement, SY measurement, and in between that's Clifford, right? It's not a Pauli. It's not going to change. It's a non-Clifford, sorry, non-Clifford. It's going to turn a Pauli into something. It's not a Pauli. And so you can sort of recreate out of a cluster state if you measure like that. And you see that you can get some sort of circuit like, which is exactly what it is. So it turns out with optics, with quantum optics, we can make those to large sizes. And when we realized that, we thought, ooh, wow, we got to see where this goes, right? And the answer is the big picture is like, yeah, it works really well. You get super large cluster states. Now the question is like, are you guys going to be doing quantum error correction on that? How is it going to be as good as trapped ions, right? Which are the, and the answer is yes, and we don't know. But we're hopeful. Okay, so the way we do it, this is like cluster state thing. We're going to work with quantum fields instead of qubits, because that's what we get in large numbers. And number two, so it's wave-like. Number two, okay, how are you going to do quantum error correction? We're going to be measuring photons. We're going to be projecting into Fock states of the harmonic oscillator, which is not trivial. Like if I give you a beam of light and you're telling me, oh, this has, you do a measurement and maybe the photon number fluctuates like in Poisson distribution of a laser field, but you know, I'm measuring 4 and not 5. And next shot, I'm measuring 5. Next shot, I'm measuring 0. And next shot, can you do this? And now we can. And so that's the big deal. And if you combine those two things, oops, okay, I wanted it to stay there. The wave and the particle, you know, it's kind of, it falls, it stands to reason that if you do non-trivial wave stuff and non-trivial particle stuff, then probably you're doing something quantum. But if you're only doing waves or only doing particles, probably you're doing classical physics. So it's kind of like one way to look at it. Okay, so I'm gonna show you the top of a picture here. You have the electric field of a quantized plane wave. And there's an operator Q and operator P there that are like position and momentum. And you see they have cosine kz minus omega t, sine kz minus omega t. So quadrature plane waves, but Q and P are like position and momentum. They're respectively A plus A dagger, A minus A dagger of I, A and A dagger are annihilation creation photon operators. So harmonic oscillator, you know, just quantum harmonic oscillator stuff. So when you have those, and that's what we measure in the lab. So one of the things with the photon number. So we have a computational basis for qubits and some arbitrary state. For Q modes, we call them Q modes. That's Daniel Gottesman who suggested that back in the day. And sort of like, hey, we don't have a better word for that. These are like position eigenstates. Eigenstate of this Q operator, which is one of the quadrature amplitudes of the electromagnetic field. And so when you measure that, you get a real number. It's like, oh, okay, so the Bloch sphere gets a little bit richer but people have figured out, the theorists have figured out how to do this. And in the end, we still want to do qubits. And of course, the probability amplitude psi naught and psi 1 become a wave function. But okay, we can do wave functions. We've done wave functions. We do wave functions for atoms. Why can't we do wave functions for, you know, and people who do quantum field theory are just like, yeah, sure. Of course, anything is a wave. So then you get the plus minus states. These actually, Hadamard transform is equivalent to Fourier transform, and you get the momentum to the eigenstate of the other quadrature. Still, but you know, those Q and P are both in the electric field and they don't commute. Right, so if I measure Q and I get an eigenstate of Q, the P is incredibly noisy. No matter what you do, the electric field is going to be complaining. But you can do some interference measurement and separate the cosine from the sine with a local oscillator interfering, doing field measurements using optical interference, and you can measure Q and P separately. You don't have to measure them both at the same time. So that's fine. So we have those things, and finally the Bell state turns into the EPR state. The Einstein-Podolsky-Rosen paper has wave functions that are delta functions, which is exactly the same as writing the state as an integral in the Dirac notation. So it's exactly the same thing. So the Einstein-Podolsky-Rosen thing, these states are completely, obviously non-physical. EPR states are like plane waves. They are not physical, but it's okay. Doesn't matter. You can always do math with things that are physical. The thing is, and you can describe any kind of physical wave as a superposition of plane waves. The thing is that we can create in the lab arbitrarily good approximation to EPR states using what we call two-mode squeezing. And so that works. So then, yeah, we'll go to qubits again. Oh, if you really want to know, oh, what about the Paulis? What about the CX, the CZ? Like everything's been figured out. Right, so the Pauli group over continuous variable is the Weil-Heisenberg group of this phase-space displacement. So translations in Q and P, basically. And for the entangling gates have been also defined in terms of the Q and P operators. Cliffords are known as Gaussian operations. Gaussian operations are defined in terms of a Wigner function of a quantum state, because it's continuous variable. So in the phase space of Q and P, you can define this generalization to the wave function, which is called the Wigner function. The wave functions is only a function of Q or only a function of P. The Fourier transform of each other. The Wigner function is a function of both Q and P. And it was invented by Wigner to do statistical physics with quantum mechanics. And the Wigner function can also have negative parts, which is really, really high, highly non-trivial. And the operation, and if it's a Gaussian, it's always positive, of course. And the Clifford operations are the operations that take a Gaussian Wigner function and keep it Gaussian. Maybe they changes, the width change and things, but it stays Gaussian. The equivalent of a non-Clifford will take a Gaussian Wigner function and make it non-Gaussian, which means it has some non-positive parts now. For example, Fock states. Fock states have oscillation that are, negative in regions. Fock states are not Gaussian states in terms of a Wigner function. And so there is an analog of the Gottesman-Neal theorem that says you need at least one non-Clifford somewhere, otherwise everything is easy to simulate classically, right? A quantum computer that's going to do anything useful must have something non-Clifford somewhere, but it's necessary, it's not sufficient. But, well, it's the same thing here. We have to have some non-Gaussian operation somewhere. In our case, it's going to be photon number detection because it projects into that Fock state basis, and Fock states are non-Gaussian. Okay, so enough about this. This is, okay, more about the field. Basically, I told you all of this before, but the classical field is at the top. This is a classical plane wave. And the quantum plane wave is what I wrote down, actually. So this one, well, that one in terms of A and A dagger is a complex exponential notation. But the thing is that you can't just say, oh, one is the complex conjugate, it's the Hermitian conjugate, and there's operators everywhere. So you can't just say, oh, I'll do my calculation, take the result, take the complex conjugate. No. There's A dagger there, it doesn't commute with A, it's Q and P, don't commute, so you have to take everything, right? So it really doubles the size of the field, so to say. So it's kind of like when you do polarization in classical optics, right? You have linear polarization. If you have circular polarization, now you have to worry about the orthogonal component of a field and how they're in phase and with each other and things like that. So, but that's fine. The thing is, why do we care about this? It's because here comes the two-mode squeezing that I told you was gonna make us some EPR entangled states. So we have nonlinear materials like parametric down conversion in nonlinear crystals, like photon entangled pairs, they use that. And what you do is that you have this kind of energy level where you have green pump photon that's annihilated and a pair of signal photons in red that's created, right? So you take a green laser beam into a crystal and comes out a pair. It's very weak. We're not like superconducting qubits. Our nonlinearities are incredibly small. That's the price to pay for being very transparent and having no losses, right? And so the Transman qubits have humongous nonlinearities, but they also have noise because, there's no free lunch, right? So you choose your poison, you entangle like crazy, and then you have noise, or you really sweat to make your gates, but you have less noise. So the Hamiltonian is like that. You can write basically the state that's created has 0 photon or 1 and 1 or 2 and 2 because the photons are emitted in pairs, right? Those two red arrows there in two fields A and B that we can separate because they have different polarizations, different frequencies of both, different direction of propagation possibly. And so we can write everything. We can write the wave functions, and the wave functions of the two-mode squeeze state are actually approximation with Gaussian terms here of those guys. So I'll leave that just there like that, but it's a good, so in the lab we can do that very well. In fact, there's DARPA programs that want us to do that on chip and said, can you do that at the level of what we call squeezing, which is this little parameter there, which basically tells us how many photons we can have maximum. Ideally everything goes to infinity, but of course, it's not going to go to infinity because that would be disturbing. Incredibly powerful, too much energy. So, but large enough that we can do quantum computing, quantum error correction above the fault tolerance threshold. And these numbers have been figured out. We know exactly what the engineering needs to be. Okay, So there we go, we need waves, we need particles. And with the wave, with the field thing, we can get large-scale entanglement in a deterministic way, no post-selection. And it's all analog to the Clifford business for qubits. And with the photon counting, we can get the exponential speed up and quantum error correction, which is analog to the non-Clifford, except that quantum error correction for qubits is actually Clifford. So it's very rich how things map. It's not trivial. But okay, we know what we have to do. We know what and what I want to impress upon you guys is that there is no, for a long time when I was working, there was some, are we ever going to be able to do that at the fault tolerance threshold? Until 2014, it was not known. Some people say it's never going to work. And as John Bell says, you know, impossibility proofs don't prove anything except lack of imagination. And then somebody came up with a fault tolerance threshold theorem for continuous variables and giving exactly how much squeezing we need. So okay. So the fields is what is my sort of wheelhouse. And the idea is like, hey, okay, we're talking about fields. There is a machine that emits light that can give you a ton of different fields, and it's called the laser. Laser is an established technology. And in particular, you know, if you have a cavity, you have two mirrors here. Basically, what we have is the resonator, optical resonator modes are going to be each of these frequencies, these are frequencies for which the wave is in phase with itself after one round trip. And if the waves does that, then all light that's being added by stimulated emission in the laser medium is going to keep adding in phase, and the field's going to build up, and you get a laser, and you get mirror partially transmitting, you get a nice bright beam, coherent, beautiful, you know, fantastic thing. And also, if the gain medium, so this is very narrow band gain medium, but if you have a broadband gain medium, like in a TISAV laser, then you can emit a lot of different frequencies at the same time. And it's called the optical frequency comb. Right? And Jan Hall and Ted Hench got a Nobel Prize in 2005 for using the optical frequency comb, stabilize the hell out of it so that it can be used for metrology and precision measurements, and revolutionize actually metrology and precision measurements. And the thing is that when the photons are emitted, they're emitted very fast, stimulated emission, but one at a time, right? And this is what it looks like. Okay, you can get megawatts out of that, but it's one at a time. So quantum mechanically speaking, it stays a classical coherent state. Now, can we tweak that and make that something more interesting for quantum computing? And well, here comes the two photon emission mechanism, right? And now instead of, so same deal, I have a cavity, I have lots of resonant modes, but now instead of emitting photons one by one, I'm putting photons in pairs. And then, okay, I had that, and I thought, oh, okay, so that photon pair entangles those two fields because, you know, you're going to get an EPR state here. You're going to get field entanglement. You can make also photon pair entanglement. People like Paul Kwiat and Tom Zeilinger did lots of things, right? And beautiful experiments, Bell inequality violations. There's just one photon pair, and maybe they're entangled in polarization, like this plus this, right? Like spins. But here, we don't do that. We just emit photon pairs, but they're correlated. Whenever I have a photon here, I have a photon there at different frequencies. But what gets entangled is the fields. So I'm not limiting myself to just one photon pair. I can have 2, 3, 4. I don't care. It fluctuates. It doesn't matter if there's noise. It's entangled. It's all good. But if this field is entangled with that field, but that field is entangled with that field, and that field is entangled with that field, what does that do? And that was 2003. I was pretty much feeling, okay, I'm going to get tenure. So now I can try something crazy. So that was the crazy thing. I said, okay, how does that work? And in fact, the first calculation I wrote, I said like, okay, somebody that Mark or somebody that Mark knows has figured that out in the 80s or 90s top, right? because it took me 10 minutes to finish a calculation. I thought, oh my God, what is this? This has been published before. And it hadn't been. So you get, so it took us 5 years from that 2003 moment to the full realization that you can get. Remember that cluster state thing? Yes, it can come from this. This machine can make that. And now I'm not the only one. There's other people in Japan, in Europe, they're doing that too. So we can do top-down machine that spits out a cluster state. So, so I wrote a review there in the Journal of Physics B. I'm writing another review, but I don't know. People are probably gonna kick me out because I'm taking too long. It's like, okay, we'll have somebody else. Yeah, but I'm working on it. But this is the paper where we did that first in 2004. And this is like, okay, I'm not gonna go through this, but there's like different bumps and they're, you know, this thing entangling the different frequencies of a column and trying to make a particular state. And then I met two guys, Nick Menicucci and Steve Flamia. Those two have a thing in common, Carl Caves. Right. Nick was an undergrad with Carl and wrote a PRL as an undergrad student with Carl Caves. Steve was a graduate student with Carl Caves and also wrote PRL with Carl Caves, of course, because as a grad student, it's kind of automatic. Nick went to work with Michael Nielsen in Queensland. Well, he went to grad school in Princeton to do string theory, got bored, shipped to Australia while still being a Princeton student to work with Michael Nielsen on quantum information. Princeton let him do it, they're clever. Said, just send us an activity report. So in 2006, he sends back a PRL. In 2008, he sends that PRL with us, where it's like, yeah, okay, so it worked out for him. Right? And the idea is that I met him at a conference in 2006 and said, yeah, like cluster states with, yeah, just like, yeah. We started hitting it off. Everybody was interested. And the problem with theories is that they can work more, they go much faster than experimentally. So I'm still working on this. And Nick and Steve have moved on to, you know, Steve Flamia has worked on everything at AWS, at Sydney, at Caltech, now at Virginia Tech. Nick is in Australia at Melbourne RMIT University, and they're working on tons of things. I'm still working on my QMOS. But we wrote down the paper where we put all those, these are the fields, optical fields, and one frequency, one polarization, and I can do all those entanglement things. I have the nonlinear crystals, I have them. We designed them, we tested them, built, they work. We're not using that but that would make a square grid lattice, which is good. It's actually rolled into a tube and wrapped around into a torus with a twist, but this is just boundary conditions because we use a single OPO, a single laser. But we had an easier way to do it. And this is an experiment that we did before it was theory. That's an experiment where we took, this is the optical frequency comb. There's 30 frequencies, two orthogonal polarizations. There's two lines there. And for each of these, we have 1, 2, 3, 4 states entangled together in a cluster state. And we know it's a cluster state because if you know something about cluster state, they are stabilizer states. We measure all the stabilizers. And we show that the stabilizers are like, the states are eigenstates of stabilizers. We show the eigenvalues and everything. And we have an extensive characterization. So we know these are cluster states. So there are only 4 types, so it's not yet the big square grid, but there's 60 modes involved, there are 15 of them. It probably keeps going, but we could only measure 60 modes at that time. So that was picked up. Let me know if I take too much time because, yeah. And then we kept working on this, and Moran Chain in the group was trying to make the big crazy torus thing. And then we were talking to Nick, and he said, oh yeah, you know, I wrote this paper in the time domain where we do some multiplexing things and interfering two combs and things. I guess you could do that in the frequency domain. And he was right. And so this is 60 modes, and this time they're all entangled together. That's 2014. And there's probably 10,000 out there that we didn't measure. We could only measure those. So these ones were sure. And this is a cluster state. If I measure that guy, it's going to affect the two neighbors here, but not the rest of a state. And so you can actually do some, but it's a 1D, you can do some gates on that, but it's kind of largely 1D, right? The 2 dimensionality is very restricted. But it's okay. It's a 1D, it's a start. We can do 2 separate ones just by tweaking the pump frequency. It's just very, very simple. So it was a remarkably versatile arrangement. And the recipe is, okay, you had 2 optical frequency columns, and you see the pairs, this orange arrows are the entangled photon pairs that are emitted, and how the entanglement is distributed between the 2 polarizations at each frequency. And then we have one polarization that's like this, another one that's like that. And then we're interfering the 2 polarizations with some polarization optics, and boom, we get the chain like that. So this is a fairly simple way to do it. And this is the kind of experimental, this is our OPO, our 2-photon emitter. There's 2 little ovens here with a nonlinear crystal here, nonlinear crystal there. These are where the photon pairs are emitted. The beams are bouncing off those 4 mirrors in figure 8, going through the crystal, in between, through the crystal, in between. There's 2 pump beams that go through the dichrome mirrors here, and here, one makes a photon pairs here, photon pairs there, and everything comes out this way. There's a piezoelectric ceramic that controls the resonator frequency so that it's exactly locked to the resonant comb. These guys, there's a piezo Peltier, that's piezo Res Peltier, thermoelectric heaters that control the temperature of that guy to a 1/10 of a millidegree. You know, there's a lot of very, but it's AMO physics, like, you know, frequency standards are, you know, the atomic clock is an AMO experiment these days. We've called atoms called trapped ions and things like that. These are the best clock. These are the most precise experiments you can make. And so we have all that thing. I'm not going to go into there. The OPO is up there. There's 2 pump lasers. Everything is phase locked. There's 3 lasers. They're all phase locked. The OPO cavity is locked also to the frequency of the laser. There's another cavity here, which is a filter for the local oscillator that's going to come here for interference measurement with the OPO comb. And we're looking at all the teeth one by one with different laser frequencies here. And we're measuring the quantum noise. And we're getting these stabilizer measurements to assess whether it's a Closy state or not. And we've done that. And this is what it looks like. We're scanning the phase of the local oscillator laser versus the phase of the optical frequency cone out of the OPO. And whenever we get, this is the shot noise limit. Whenever you go below it, you have squeezing, you have an eigenstate of something. And the way we do that, we do 4 field measurements so we can actually measure the particular 4-edge graph link there between 2 regions. So 4 Q modes together. It works the same thing exactly as a qubit cluster state. And then we go on to the next link, and every time we see the squeezing and we know we have a cluster state. And if you measure the wrong thing, so for example, what we're measuring is the edges between those highlighted 2 modes here and 2 modes there. There's no edge that connects them, right? So it's like you're measuring half of a belt state, right? The spins up and down is completely random. It's maximally noisy. And this is what we see. We see noise levels, there's no squeezing, and it's above the shot noise. So it's excess quantum noise, and we check it is quantum noise. We can tell. And it tells us that we're measuring something that's entangled, but you know, that's not connected. There's no entanglement. So we can do those thorough. We did that for all of the modes there. So I'm showing half the measurements there, but all the squeezing is consistent across the board, is all the same. And we think we have 10,000 of these, but we only measure 60. And this is what Xu is doing. Well, he's doing the same thing. Remember those little things. So he has those racetrack resonators. So you go through waveguide and you're tangenting another waveguide. So you can tunnel light by frustrated total internal reflection. And then the light goes in there and resonates the same way as it bounces between the 2 mirrors, right? And that resonance, there's a nonlinear effect also that creates photon pairs. And those photon pairs are actually coming out, and you can measure those photon correlations. So instead of 3 dB of squeezing that I had, which is a 50% quantum noise reduction, here it only has 1 dB. for reasons like doing things on chip is very different from doing it in free space. In free space, I realized, oh, I have a problem, I change the mirror. On the chip, you have a problem, you refab the chip. You go back to the fab and you work and you wait for your turn and then you work and then you make 10 of them or 100 of them. And then you hope that one of them is right. So, but once you have it down, the fab is going to be incredibly powerful because you can make the same thing over and over and over again a gazillion times, right? And now I can do my experiment a gazillion times on I need a warehouse with 20,000 grad students. And they're gonna unionize and they're gonna go on strike and they will be right. They will be completely right. So this is what we're gonna do. So I'm gonna talk about photons a little bit. And the idea is like, this is something that the late Sebunam, who left us too soon last year, pioneered at NIST, is transition edge sensors, which are superconducting detectors that are sensitive to the photon number, which is a beautiful thing. So what we want is in technical terms, a POVM that's pure in terms of the Fock state projector. Because then we're projecting into Fock states which have non-positive Wigner functions, and this is a non-Gaussian, i.e. non-Clifford gate that we can make out of that. So Thomas Gerritz and Aaron Miller were helping at the time. Aaron Miller was an academic at Albion College. He's now co-founded Quantum Opus that makes those superconducting detectors. And so the way it works is that you've got like a cryogenic fridge here. I'm talking 100 millikelvin. It's seriously cold. And you have a piece of superconducting tungsten, and some photons are arriving here. And when the photon is absorbed, it transfers h nu of energy. That's going to be heat. It's going to raise the temperature. Right? There's a weak thermal link here so that we can see the temperature change over a short period of time, microsecond. So what happens is that, well, this is resistance versus temperature of a superconductor. At high temperature, it's a metal, it's tungsten. It's normal resistance, and then you get to the transition. So that's the very sharp, and the transition ebb, and then zero. And so we work here, right? And with the photon, boom, we get a little bit of resistance increase that can be picked up by a magnetic induction circuit that involves a squid. And this is the signal that you get. You get a rise time of about 100 nanoseconds. And then eventually that heat is dissipated and the cooling through the weak thermal link takes over, and that goes back to the zero resistance. But if you have more than one photon at a time, you climb twice as high, 3 times as high, and you can get these different peaks at different heights that tell you whether you had 1 or 2 or 3 photons. You have to make sure that your detection efficiency is 100%, because otherwise you thought you had 3 photons, in fact you had 5. Right, or 4, and the Fock states are orthogonal states, so it's bad. You thought you projected into one state, but you're in an orthogonal state to it. It's really bad. So you have to experiments have to be perfect, and we've improved that thing. This is Miller at work in the lab before Christmas, 2 or 3 years ago, and this is laser pulses. Poisson distribution hitting the transition edge sensor. And you see 1 photon, 2 photon, 3 photon, 4. And you see by 8 or 9, then the peak doesn't increase anymore. Why? Because the resistance is now metallic resistance, right? You're completely out of a transition edge. And so then anymore, you got 17 there early on, right? There's the same peak, but you see that the cooling tail is different because the amount of heat is different by integer number of h nu, right? It's quantized. It's quantized heat. So the cooling times are different, and with the guys at Jefferson Lab, we made us some real-time integrator using FPGAs, which is like, oh, you're talking about what, microsecond? Okay, we work at gigahertz speed at Jefferson Lab, so that should not be. So that wasn't hard. But we put a nice paper in Nature Photonics because, well, we saw a paper by Rich Biritella Chris Gary and Paul Alsing, where they said, well, if you sample out of a Poisson distribution, the probability of getting an even or odd photon number is pretty much 50-50. If you're, well, it goes down, residual bias goes down as exponential of the minus twice the average photon number. And so we had an average photon number of 57 that would give us this, which we couldn't see the residual bias that we had from experimental data analysis was 10-4. So, but you know, this is the blue is the histogram experimental, and the red is the so it looks like a Poisson distribution. Okay, we proved that the laser has a Poisson distribution. That's not new physics, but 100 photons got us into nature photonics. And it's like I told my student Amer Hossam Eldin, who is one of the co-author with Miller, said, like, you have to realize how lucky you are. You have not had to worry about any losses here. Yeah, there were lots of losses. We didn't care. That's coherent states. Another student, Raj Nehra, who's now professor at UMass Amherst. Miller and Raj were my two top students, and they used photon number resolving detectors for quantum tomography in various number of ways. These in particular are the one photon Wigner function. Experimentally reconstructed, that's not too bad here. Almost looks like a textbook picture. So, and you know, this is the part that's negative here. There. So we got some really good, then the tomography still has an exponential overhead, but the quantum optical tomography, the reconstruction of a Wigner function is much faster if you work with photon numbers than if you work with homodyne detection like Mike Raymer originally proposed. And he's still done because it works really well. Okay, so we're working with Joe and Andreas on taking those photon number resolving detector and making them room temperature. And to do that, and that's more like what the company is doing, to do that, we're not going to use superconducting materials. We're going to use semi-conducting materials. We're going to use avalanche photodiodes instead of transition edge sensors. Okay. And so that's work in progress, but we're very happy with the way it's going. And then you put the wave and the particle together, maybe you get a quantum computer. So I told you, okay, I told you qubits, this is the QMOS. You know, I said, no, we're going to get qubits again, and this is what it looks like. So this is the Gottesman Kitaev Presqu'île state. And this is the wave function of a state that looks like a comb, but it's not a frequency comb. It's a quantum comb state, right? So wave function is multi-peaked like that. So ideally, it's a Dirac comb, but of course, those things have to be, well, this is Gaussian envelope and no Gaussian teeth. And the width of these Gaussians is the quantum noise reduction we can get on the squeezing. So remember when I showed you my entanglement data where I had 3 dB and things, that's directly related to the width of that teeth, the tooth. But I haven't told you how to make those states because they're really hard to make. But assume you can make them, then you have this guy, and you have that guy, and you see that they're like, you know, straddle, so they're orthogonal, right? The product of the two wave functions here is going to be 0. Okay, you got qubit. Actually, if you are very squeezed, you have more room for more. You can make a qubit out of that. Right? And encoding a qubit in an oscillator, they had encoding a qubit in an oscillator as a title, and Fils-Rivet put qubit in there because qubit was a neologism at the time. It was a new word, and you can't put new words in titles. And so they still wrote qubits, but in the paper. So those states would be great because you can show that with those states, you can correct not only the qubit errors, you can do quantum error correction, you can do everything qubits do. You can do that using exactly the same analogy that I showed you about Pauli's and Weierhasenberg and all these things. So if I want to do a Pauli on those states, I just do a displacement. And you can also correct the errors on the Q states, the little drifts of the continuous variables, which is a really big deal. And Nick Menicucci in 2014, that's the same guy, showed that if this is squeezed enough, then you can be fault tolerant. So there is a fault tolerant threshold for that architecture. And it was 20 dB squeezing, which is kind of a lot. Hasn't been reached optically, but now new work after Menikuchi's existence proof has shown that around 10 dB squeezing, which has been realized, the record is 15 dB right now optically. We're trying to beat it in my lab, but I had to move the lab to another building because the university told me to. So now we rebuilt the lab and we're trying to do this. So these are things that they're fairly recent results, right? So the dark horse thing. So, but this is not just an optical thing. GKP states have been made in phonon fields. Bosons are bosons, right? Don't have to be photons. So the phonons that describe the vibration of a trapped ion qubit, that's a field, that's a boson field that's coupled to the trapped ion qubit. And they made that in Jonathan Holmes' group at Zurich, ETH Zurich. They made that into a GKP state, which has some good amount of squeeze. You can see that's the Wigner function. Here, this has been obtained at Yale in Michel Desbordes' group, where the Transman qubit is coupled to a cavity field, a microwave field, and they put that into a GKP state. And in Japan, Akira Furusawa, at the beginning of the year, did a GKP state with light, so that's the first one. And the squeezing is a lot less, so that state is, very preliminary, but these are negative parts of the Wigner function, and the Wigner function is a grid. That is a good beginning, and optics is way more scalable than trapped ions, so, it's dark horse. Don't rule them out. So, meanwhile, we are very pleased with ourselves because we have some ways to use all the cluster states we can make that I showed you some examples of, combined with, measurement-based quantum processing, really alternating balance and modal detection and photon number resolving detection. You can engineer quantum evolution to get that kind of GKP qubit smack down. So you have a square grid Q-mode entangled cluster state, and you have some branches that are GKP factories, and you can do quantum state preparation, boom, 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 and then you land a GKP qubit. Also, you have to have branches everywhere. So it's kind of a 3D lattice. The vertical dimension is kind of a state preparation, quantum processing, and then you land those things. And now what you have is qubits over cluster state. So you start to. So this is still a proposal, but we've done the full theoretical study to show that this works. And there was a collaboration with Nick Menikuchi and Ralph Alexander and Carlos Miller. It was an idea by Miller. And then finally, the last thing that we did, and this is Emmanuel, who was an undergrad at UVA and wanted to, I realized every year he would send me an email, can I do quantum computing with you? And like, then I said, oh, have you taken quantum? Sure. But then I said, that name is familiar. And then I went back to my email. Every year, he was sending me an email. And the first time I said, oh, your first year, yeah, you have to take quantum. And then the second, oh, are you taking quantum? Have you? And then the third year said, and I was consistent, but like I had forgotten. But I'm so glad he came because he was a double major in computer science and physics. And we wrote a paper together for his undergraduate senior thesis in computer science on quantum optics and graph classification with boson sampling. And then he went to work with Buzal and Hamilton, and on his spare time, he works with me. And so this is our latest. We have another one in preparation about quantum state preparation with machine learning. So the idea, and that's the last thing I'm going to talk about, kind of late. If you have like some non-classical state of light coming in there in a pulse, this is a simple optical circuit where you have a beam splitter, so reflect some of the light, transmit some of the light. Here you have a photon number resolving detector. Remember, these are important, right? So we just randomly measures the photons randomly, measurement, right? Boom, wave function collapse, boom, Fock state, whatever. Sends that to a neural network. Neural network can, okay, then the light, this is 100% reflecting for now. Light goes around, comes back, interferes just in time with the next pulse. Interference, split, photon number resolution, stand back. And every time what's in there, we evaluate the fidelity with a target state, that one that we want. And we just let, and we don't know, calculating this is already complicated analytically, but we don't try. We give that to a neural network that's trained by reinforcement learning. Just like make that fidelity 1, and fidelity to the power of 50, so that to make it more dramatic. And what the network can do, the agent can do, once a neural network is trained, is can change the transmittivity here, change the type of squeeze state that it sends there, and the information is the photon number there. And you figure out your own rules. I don't know how it works. Just you learn from me. And so, this is the state I want. This is a cat state Wigner function. This is a squeeze cat state Wigner function. I want one of these 4 ones. I don't mind whichever is good. These are precursor to the GKP states. Once you have that, you just need to do one little interference, optical interference, deterministic operation, and boom, you got a GKP state. So this is like, okay, if you can make those, I'll be happy. And this is what it did. So this is the number of events. This is the fidelity. This is 100% high here. And I looked at all of them individually. There's like, once the network is trained over 7 million of iterations, then you let it run for 50 steps at a time, 1,000 times, different times. And these are the statistics for all this. I'm just going to show you this. And those states, even those guys like a little bit lower fidelity, 90 plus, they are all squeeze quantum states, squeeze cat states. They have slightly different spacing, so the fidelity doesn't work out that well, but qualitatively, they're the real thing. And we know what they are from the sequence of events in the iterations, the different parameters. We keep track of everything, so we can even make a lookup table, say, oh, okay, you did those reflectances and you measure those number of photons, that's the state that you got. Because, it's deterministic. It's just sampling, but we know what's sampled all the time. 98% of the time it works. And none of the proposals that were put out there by the competition could go above 0.1%. So we think there's only Team Ralph, because Team Ralph is. Team Ralph put out something at the same time as us that was also pretty good. But they need, we only need non-Gaussian detection. They need non-Gaussian input states. So they need 2 non-Gaussian things. So it's a little bit harder. So anyway, qubits without qubits. This is what it was about. And so we don't need the physical qubits. We can make them out of fields, out of these GKP wave functions. Everything is measurement-based quantum computing, so which is nice because measurements is what physicists do best. This is what we're trained to do, measure. Not quantum gates, measure. And we're trying to put that on integrated optics. Machine learning is really interesting, but okay, this everybody knows. And when we look at what AI does, actually, we got some insights for how to do things without using AI, like design experiments that we wouldn't know how to design. Just looking at, oh, this is what works for the agents. Like, all right, let's do this instead. So it's not going to work all the time because it's not an iterative process, but it's just 1 step or maybe 2-step process, but it's got already a higher success probability even. So we're looking at other things like other quantum states for quantum simulation, and we've had results that we haven't published yet, but that is going to be relevant to the quantum simulation of quantum field theory. So we're happy about that. And this is there's 2 ways of making quantum computer. You can go bottom up, you knit up your cluster state, or you can go industrial. Thanks. And I know you have questions. So.
What's relation? Is there a relation your model with the coherent Ising machine?
So the coherent Ising machine is not quantum.
Okay, yeah, I know.
And the workhorse is an optical parametric oscillator. So it's the same machine emitting photon pairs. It's really clever. I love the coherent Ising machine. So I'm not dissing. I'm really like, when it came out, I was so enthused. But yeah, it's not the same thing at all. It's just this really clever way of finding the absolute local minimum coming from below. The R machine is really meant to be a quantum computing processor in a very canonical sense.
You mentioned about this 100 photon where you saw this Gaussian distribution.
Poisson,
The
yeah.
So Poisson is like,
It's log, so it looks like a Gaussian, but it was a log scale.
oh, so it's like, okay. So that's why I confused, because like what happened if like, because if close to zero, you cannot have minus. The number of detectors, it seems to be like normal distribution.
Oh yeah, no, yeah, no. So we just no, it's completely a Poisson distribution. And it's just, it was just kind of a, you know, us. We put three detectors at 35 photons each. We really try to get as many distinguishable photon number signals per detector to try to get a triple digit. So it's just all in the 100, but there's nothing else is new or interesting. And it's just a Poisson distribution from a laser, and like it was all very expected. But yeah, the histogram is presented on a log scale. So in fact, when you look at the things, come back. So see, this is many orders of magnitude below 10⁻8. So it's just like, okay, but we still can, you know, have things that the noise is so small on the superconducting detectors that.
So you have the lattice now with the GKP states in principle anyway.
In principle.
In principle. What kind of measurements do you do on that to do the measurement-based quantum computing? How do you measure the GKP states?
So I'm checking myself. So if you do Paulys, you just do displacement measurements. So we do homodyne measurements. That's like, long story short, homodyne measurement. Once you have a GKP state, everything else is Gaussian, which is remarkable. I mean, in principle, it's not wrong, but it's, you know, it's not necessary, right? It would be sufficient if you have you have a non-Gaussian something, but is that one going to be good enough? It's never guaranteed. The layer of sophistication is that the quantum error correction on the cluster state, which is qubit, including qubit for Rasendorf, is foliated cluster states. So you have to have a 3D cluster state, which is a qubit centered, and foliation is a thing that was all the CSS error codes can be foliated. And so then the cluster state is not used as a quantum processor to make gates. It's used to encode, like, for example, the Kitaev toric code, which is what Rasendorf did, because that's the highest threshold one, it's the easiest one, can be foliated into that cubic face-centered qubit thing that, and so then the cubic, the cluster state is a 3D cluster state that's just there to correct errors, and you measure stabilizers to do the Kitaev. And then how do you gates? So then Rasendorf came on top of that, say, well, you have some defects in there that you braid, and you make the gates by braiding, or there's something else called lattice surgery that is also can be used to make gates on that. So that's the whole picture of the thing. Nevertheless, all the measurements remained homodyne measurements once you have the GKP.
FPGA dual fabrication or?
So FPGAs are made by those guys. So Jefferson Lab electronics team. So we had a nice collaboration, and
What about the programming when it goes into the USB two programs?
We are not going nowhere near the FPGA programming. I know people who did. They survived it. Not me. But yeah, no. So it was a collaboration with government lab.
The USB component is not gonna be an easy task to manipulate all the circuitry.
Yeah, so in that case, it's just a very, very simple task of integrating the measurement signal. So that's all it did. So it's a very well defined.
The signal.
Pardon me?
The USB is not like the most intelligent device to communicate with that FPGA.
So USB,
Yeah, the USB, you connecting the FPGA to the USB controller on the laptop, right?
okay, yeah, I don't know the details of that. I just know it works, but yeah, I have no knowledge of the details. They made a black box for us that spit out some numbers for the areas.
It costs a lot of time to build that black box.
Well, the guy worked on it for a few months, yeah. That was a project. It was funded.
Calibrating that is nice.
I love collaborating.
It's probably not a fair question, but,
Oh, it's okay.
the only other optical computing I know of is Xanadu. And, how are they different from what you're doing?
We're very, very close.
We're very close.
We're very, very, very close.
Xanadu, it's a Canadian company.
Do they have an optical computer or?
Yes. Well, they're working on it.
They don't.
They don't.
They have,
Something.
they did boson sampling. They did very limited demonstrations with a few modes. The IonQs are trapped on the big company that's photonic quantum computing is PsiQuantum. But PsiQuantum, that they're very secretive.
Quantum.
Yeah. They have an experimental paper out like a few months ago where they gave no details, but they made lots of claims about, okay, so there might, but you know, the details in the supplemental material to be published at a later time. Yeah, okay, all right. So you guys are industry, so you know, it's like, so Xanadu, I'm not gonna diss Xanadu, but they're very strong in theory. They've done a lot of theoretical advances. They rely on commercial hardware, except for transition edge sensors that they got from, say, Wunam's group at NIST. So but the problem is that their chips and everything, and nothing is good enough anywhere. And you got to make the hardware better. That's what PsiQuantum is doing. They got into a major, and they're not saying anything about what they're doing, but they spent a ton of money on foundries and cryogenics because they use superconducting photon detectors, and they're just gonna, right? And that's what we want to make room temperature photon detectors because but they went to the UK and they're building the mother of all cryo plants. Just to, and it's okay. I mean, like, you know, you can build an ENIAC and the ENIAC worked, right? That's all we care about. So maybe we're more about the PC than the ENIAC. Well, time will tell, but yeah, that's the hardware has to be better. That's the big thing. At least good enough that quantum error correction kicks in at the fault above the fault lines for sure.
In progress, in progress, in progress.
So I just, okay. Thank you, thank Mark too. Like my pleasure to be here. Thank you. I see that.